All right, everyone, welcome again to another Swim Smart webinar. I was about to say exclusive. It's not really exclusive, it's for everybody. So we'll keep this up on the channel for a little while. And if you find value, then feel free to share it with like your swimmers, your parents, your assistant coaches, whoever you think would benefit. Like and share, of course, we always appreciate. And because you have managed to come from such a distance to come listen to my amazing monotone voice talk about something that probably seems insignificant, but hopefully I'll convince you otherwise. Please use our code webinar20 for 20% off the website. So anything on the Swim Smart, I think anything. It may not apply to t-shirts, but I think it applies to everything else. But been having a lot of big orders lately and very thankful for everybody's participation in our little side hustle here. And let's get going. You know, you guys came to learn about lungs, breathing, acid control. Let me get this PowerPoint up, and I always have to switch it because I'm not technically savvy. I'm a little technically savvy, but not great. And I'll get my pen out here. Okay, I like to use the pen. So this is kind of what we're going to go through today. It goes from least complicated to most complicated. So first thing we're going to talk about in this like lungs section is how do we get the air to the blood or next to the blood, and that's where the gas exchange happens and what's involved in that. What does it mean on deck, right? My goal is always to give you at least some practical points, so taking you from the kind of biology, chemistry, science to the pool deck, and that way you can teach your swimmers, you can teach your parents, and then they'll believe you as a coach, and you build trust in your team that way. Second thing we're going to talk about, why do we feel air hungry? So that feeling of I need to take a breath, that's called air hunger. It's a fairly complicated system, and there are a couple details that are important for us as coaches to know, especially when we're writing workouts and when we're giving advice to our swimmers, like before sets, before races. And then the last thing, and this is kind of where we're going to dive into a little bit of chemistry, dealing with the acids. So like, why are we breathing? And there's a couple, this talk, what I'm going to try to show you is that breathing is like an exhaust mechanism. So cars take in oxygen through the front, right? They take air through the intake valves, or I'm not a huge car guy, but they take air from the front, and then there's an exhaust in the back. Humans operate differently. Our intake and exhaust are in the same place, right? So everything happens through our lungs, and it's almost, if not more important, that we breathe for the purpose of exhaust rather than air intake, okay? So we're going to go through those details at the end. So let's get started with the simple stuff, a little bit of anatomy and biology here. So these gray pyramids, these are my lungs here, and the red arcs, these are diaphragms, right? So when you're just expired and you're just relaxing, the diaphragm is relaxed, and when you take a breath in, that's when your diaphragm contracts and it pulls down and it creates that extra space, and it pulls the air into the lungs. Okay, so the rib cage, for instance, most people think that the rib cage exists to protect the heart and the lungs. Well, that's not, I don't know. I don't think that's necessarily true, actually. I'm going to try to convince you. So why, if the ribs are so protective, why don't they go all the way down into the abdomen? Is the liver not worth protecting? Is the spleen, kidneys not worth protecting? No, they're all worth protecting. The reason that you have a rib cage is so that when your diaphragm pulls down, your chest cavity doesn't collapse inward, right? And you want the air to come through the mouth and the airways down into the lungs. You don't want the chest cavity to collapse. And we actually see this problem in the hospital. People who have multiple rib fractures and they're broken in several places, when they take a breath in, instead of the air going in through the mouth, their chest will just collapse to take up the extra negative pressure. And they get no air in, and then they have to be intubated and fixed. It's called a flail chest, if you want to look that up. So that's actually something, so that's why the chest that's why the ribs exist. They exist to create a support cage so that you're pulling air in through the right place and not collapsing the chest inwards. When you're at rest, when you let go of the breath, so you take a deep breath in, and when you let that go, no muscles are being used. You're just kind of releasing the diaphragm, and the recoil of everything pushes the air out. Things change when you're like working hard and you're during a workout. Way more muscles kick in than just the diaphragm. So now we've got these intercostal muscles here on the side. You've got pectoralis minor. So pectoralis major is what we're all used to seeing. There's a little muscle that goes from the top down to the ribs, and it pulls the ribs up to help expand the space. You've got some neck muscles that get kicked in. You've got ab muscles that kick in. So now you've got a whole range of muscles that kick in. And why is that important? Because at rest, 2% of the oxygen that you breathe in goes to these breathing muscles. But when you're at a full workout and a full sprint, these muscles can eat up 15 to 20% of the oxygen that you're breathing, which is a huge amount. I mean, a 1/5 of the air and the energy that you're expending is just to move the air in and out, in and out, in and out. And these muscles, like all other muscles, they need training. So the more you do this, the better they will be. The more capillaries they develop, the more mitochondria that they develop, the more efficient they become. And so, if you have swimmers that are new to the sport, or they're coming in from the off season and they're like, I can't catch my breath, I can't seem to breathe, you can teach them. You can be like, look, when you work out, you're using way more muscles, and those muscles, like your legs, like your arms, like your abs, they need to be trained up. So work through it, make your body suffer through it a little bit, and they will improve. I am watching the chat, so thanks to Swim Talk. Is this going to be available later on demand? Yes, this is going to stay on our YouTube channel for at least a little while. I seem to forget to take them off, so it's probably going to be on there for a few months. So yes, please feel free to share. We're happy to have this information go out to people who are interested. And if you guys have questions as we're going along live, throw them in the chat and I'll try to get to them and stay on top of that. So before training, you have wimpy dinky little diaphragms, and after training they get all beefed up and strong. Okay, not really. I mean, they don't change that much, but they do improve. That's what we want. Oh, Dana Abbott, thank you. Okay, so alveoli. So what's the point of getting the air into the lungs, right? This is where we want the air to end up. We want them to end up in these alveoli, which I think most of us maybe remember that word from high school biology. There's these little kind of sacs, and they're just full of air. So when you look at a CT scan through the chest, it just looks like air, basically, because most of the lungs is air in this area. One thing I will mention is that the airways, so the tunnel, this bronchiole, it's kind of a tunnel where the air comes in from. So it comes in through here, and there's little amounts of muscle around the tunnels. So the lungs can actually control which parts of the lung are getting air and which are not. It's not that important for us to know. The one thing I mention this is because people with asthma, if you have swimmers with asthma, these muscles get really, really thick and really fat, and they can stenose and they can narrow this tunnel, and it actually doesn't create a problem of the air getting in, it actually creates a problem of the air getting out. So they actually have air trapping, and they same with if you have family members that have COPD, it's the same. They kind of have the opposite problem, where their walls are weak, but they both end up in the same problem where they have air trapping, because if you can't get the air out, it's as if you're not being able to breathe, right? So there's kind of, I don't know, some medicine in there. Sorry, I bring work into the swim pool every once in a while. So this is the goal, right? We want to get those muscles to pull the air into the alveoli, and this is where the magic happens. And for those in the chat, I will show you where you can get video sections of this and much more at the end. So when we're at the capillaries, or at the alveoli, the air and the blood can come kind of flat together, and that's where gas exchange can happen. So this is my great drawing of an RBC, red blood cell. Sorry, I can't use my mouse to write very well, but okay. So this is a spent RBC. So you see it's all full of CO2. There's no oxygen in here, and it's coming towards the alveoli through the pulmonary arteries. None of these are important. I'm just throwing in extra words here. And then once we're close to the air, you can get the exchange, right? Because the air and all these gases, they want to balance out. So if you have a high level of CO2 one place and a low level of CO2 another place, the natural diffusion is for it to balance out. So the CO2 goes from the red blood cells, it goes into the air, and then that's what you breathe out as, you know, high CO2 air. And of course you breathe in the alveoli, you have a lot of oxygen, so the oxygen goes from the alveoli into the red blood cell, and this is what we call gas exchange. And then this red blood cell continues on full of O2 to the heart to get pumped out into the rest of the muscles and the brain and the kidneys and all that jazz. So this is kind of the magic of the lungs. This is what they're here for, to do that gas exchange. One thing I'll say right now before we get too far on, basically this is a very overbuilt system. So your lungs have way more capacity, at least in normal and even in athletic people. Your lungs have way more capacity to do this gas exchange than you would ever need. So they did experiments where they had track athletes run at all-out sprints, and then you would think like their heart rate's at 210 beats per minute, their muscles are, you know, maxed out, and then they told them right at the end of the race, I want you to voluntarily breathe even more fast, more deep than you normally would. And they were all able to do that. So what that tells us is that this system is way overbuilt. And there's a reason this is overbuilt, because if any of us know, if you stop breathing even for a few minutes, you'll die, right? So your body has so what I'm trying to get at is every red blood cell that passes through your lungs is full of oxygen. It's at 100% capacity, even at maximum like training level. Okay, there's a few detailed examples of super elite athletes where that percentage will drop into the 90s, but the basic point I want you to take away here is that all red blood cells get full of oxygen as they pass through the lungs. And that does kind of become important later on in the show. There are some changes that happen between rest and exercise and before and after training. So if we look at the blood flow to the lungs during rest, so we're not sending a lot of blood to the lungs. We're not sending a lot of blood out into the muscles. Things are just kind of stagnant. And so you don't actually need a lot of your lungs to have blood flow. So most of the blood flows to the bottom portion of the lungs, and the upper portion, just air goes in there, but there's not a lot of gas exchange because those blood capillaries are closed off to that area. But once you warm up and you get some blood flow going and you've moved things around, and we talk about that in cardiovascular talk a little bit more, but there's more blood. So now we start opening things up to the upper lungs and the lower lungs, and so we're maximizing the gas exchange a little bit more. Again, this is the reason I point this out, is because some people out there are suggesting that warm up is not necessary and you just need to kind of loosen your muscles up, jump on the blocks and go. Maybe for a 50 you could get away with it, but I think anything over a 50 you're going to be at a disadvantage because you're not taking advantage of this and many other reasons. So another thing that we can show is the capillaries before and after training. So if you're like me and you spend all day sitting down at a computer and then you go for a morning workout with the master's team once a month, like I did today, I have very few capillaries surrounding my alveoli, and so I'm not very good at gas exchange. Whereas if I trained for a couple months or a couple weeks, I'm going to get way more blood flow and the ability to do gas exchange. And so my whole body is going to be much more efficient at training and at racing. So things can be trained and can change even in the lungs. Like we all look for, shredded biceps and abs, but the lungs, they get trained too. We shouldn't forget about them. Okay, one last point of physics before we move on to the second section. Remember, your lungs are basically big bags of air, and you can never really push all the air out, right? If you were able to push all the air out, your chest, like your thorax, your chest would have to squeeze shut in order to do that. So it's never possible to get all the air out. There's actually quite a bit of air left in there. And remember, air floats. So lungs are big, it's like those floaty balloons that you put on little kid arms, but it's inside of your chest. And that's why, especially new swimmers, they always want to go vertical, and it's difficult for them to push their chest and head down. And that's why we try to get them to look down so that they can properly float flat in the water and bring their legs up a little bit, is because their lungs are full of air and air wants to rise in the water. So hopefully that gives you another tip and point for you to share with at least new swimmers who are on the team. Maybe more useful for master swimmers. Master swimmers tend to swim uphill a little bit. Okay, why do we feel air hungry? So we're going to get a little more complicated. So the term that you're going to hear is air hunger. So this is the feeling that you need to breathe, and it's a very complex system because there's both involuntary and voluntary mechanisms, right? So when you go to bed and you fall asleep, you're not thinking about breathing. It's happening on its own. But if you're up on the blocks before a race and you're taking in these deep breaths, you're doing it on purpose, right? So the software that controls all of these feelings is very complicated. It's very redundant. But what we're going to talk about are these three big factors. So what are the things that make you feel more air hunger or less air hunger based on their levels? So CO2 in the blood is number one, oxygen is number two, and pH, or the acid in the blood, is number three. pH and CO2, we're going to see these are almost interchangeable. And then oxygen, we're going to see how all of these play out. They all kind of play a little bit different role, and they have different sensitivities into how they change our breathing. So let's look at CO2 first and see how it changes our breathing. This is the most sensitive. So CO2 changes very rapidly and very easily in the blood, in the blood. So this gray line here on this chart, the gray line is the CO2 level in the blood, and the green line is air hunger. So if the green line is going up, you feel more hungry for air, and if it's going down, you feel less hungry for air. So let's take an example here. Let's say our CO2 is at steady level, and then we hold our breath. So you hold the breath, and your CO2 level starts to slowly rise in your blood. And as it's rising, immediately you get a rise in air hunger, right? So that's why holding your breath is hard, because your body says, hey, the CO2 is going up. You need to breathe, you need to breathe, you need to breathe. And if it gets so bad, it'll just start breathing on its own. Okay, so then you start breathing and the CO2 goes down and the air hunger goes down. Well, what if we did the opposite? What if we hyperventilate? What if you voluntarily breathe more fast and more deep than you actually need to? Well, then your CO2 is actually going to go down, and so is your air hunger. So if you hyperventilate before you do a long breath hold, you're not going to get that feeling of needing to breathe, and you're going to be able to hold your breath a lot longer than you normally would. And I know a lot of you right now are thinking, well, why did they tell us not to hyperventilate before those things? And we're gonna get there. So first, let's look at oxygen and breathing. So oxygen is not as sensitive as CO2. So if we took the same graph and let's say you start holding your breath here, your body is still using the oxygen in your blood even as it's circulating. So your oxygen goes down, but you can see there's a big delay here, right? So by the time your oxygen levels are low, you're not feeling like you need to breathe just yet. So the breathing, the air hunger comes much later than it does for CO2. These lines are almost identical. They follow each other. Whereas these lines, there's a bit of a delay here, okay? But once your O2 is low, you do get a big rise and a big kick in that air hunger. So this will be important soon. Right here. It's going to be important right here. Why don't you hyperventilate before a hypoxic set? So why do kids, we hear about this every once in a while, another kid passed out in the pool. They were doing a underwater set or something. And why is that dangerous? Okay, it's a little bit of a complicated chart, but hopefully things will make sense. First thing I'm going to have you look at is the oxygen line here. So this is the blue line. And remember what I said before, all the red blood cells that pass through your lungs, they're at 100% oxygen. So even if you hyperventilate, with hyperventilating or without, you cannot change the oxygen level in your blood. So that's going to be the same, and it's going to run out at the same time. So when your oxygen levels hit this 0 or near 0 mark, that's when you pass out, right? Because then your brain doesn't have enough oxygen to make ATP and to stay on and to keep the lights on. Okay, so now let me erase some of these lines. So does that make sense? So whether you're hyperventilating or not, your oxygen is going to run out at the same time. Okay, what about CO2? So here are the two charts. If we just do the hypoxic set without hyperventilating, well then our CO2 is going to go up, and so is our air hunger, and it's going to stimulate us to come up to the surface and get a breath. But if we did hyperventilate, well then we're artificially pushing down the CO2 and we're artificially pushing down the air hunger, and by the time the air hunger is high enough to get us to breathe, we've already run out of oxygen and we've passed out, and coach is jumping into the water to save us, okay? So this is one reason why it's not a great idea to get kids to hyperventilate before they do a hypoxic set. I will say that's maybe a little different than hyperventilating before 50 freestyle. So a 50, most people are going to hold their breath for the majority of it. But luckily the 50 is relatively short. So number one, so we're not going to really reach this 0 point, at least for a semi-trained athlete. Number two, as you're sprinting, you're going to generate a lot of CO2 and a lot of acid. So we're not going to be down here with those levels. They're going to start rising pretty quickly. So our air hunger is going to kick in early enough. And then number three, air hunger is also stimulated by just like joint movement. So they've done studies where just moving the arms, if you put your arms in a machine without your muscles like doing anything, that will stimulate your breathing to kick in. So we have several more stimulants to air hunger when we're sprinting. But if you do a hypoxic set where you want kids to just swim really slowly underwater for as long as they can, I think that's where you get into trouble and kids passing out. So that's the science behind it. Hopefully that made sense. I know it's a little complicated, but the recording will be up, I guess, if you want to watch it again. Okay, so pH, that's a measure of acid in your blood. This has to stay in a super, super tight range. This cannot change very much. CO2 can go all kinds of places and you'd be okay for a little bit. pH really is in a tight space, so it can affect your air hunger a lot. And what we're going to see here in this third section is that acid and CO2 are almost interchangeable. So the more acid you have, the more CO2 you'll have, and the more air hunger you'll have. Okay, one quick drink, and we'll get to this last section. So this is the section where I try to convince you that the exhaust part of your breathing is more important than the oxygen intake part. Or at least it's a very big and important part. And this can really change how we think about race strategy, especially for the 100, 200 races. But before we get into that, we have to understand this equation. So sorry if you're getting nightmares from chemistry class back in high school, but so on the left side here, we have CO2 and water. We don't have to pay attention too much to the water part. Just the CO2 is here, right? Carbon dioxide. And this can be exchanged with carbonic acid, okay? And that can be exchanged freely, you know, they go back and forth, freely exchanged with hydrogen. Hydrogen is another, you know, acid is hydrogen. So whenever somebody says acid, they're talking about the hydrogen concentration, and bicarb, okay? So why is this all important? So these are all interchangeable. They're all going to, and why this is important, let me erase all these lines and clean this up a bit, is that the amount you have of any of these depends on if the inputs are changing on one side. So let's say I start holding my breath and the amount of CO2 I have in my blood starts to go up. And because it's going up, there's an imbalance in the equation, right? So as that happens, CO2 will start to become carbonic acid, and then that will start to become acid in my bloodstream, right? So, and the opposite happens too. So if I'm sprinting and I'm using glycolysis, the engine that produces the acid will start going up really, really high, and that will in turn move everything off to the other side of the equation, okay? So in the muscles, and we'll see this again here, I won't leave, we'll do a couple examples here, but in the muscles, we're really heavy on acid and even a little bit of CO2. And so these are starting to go up. But in the lungs, the opposite is happening, right? We're blowing off CO2, so the CO2 levels are really low, and this has to backfill from the other side of the equation. So we're transferring acid into CO2, and then that gets pushed out into the lungs, like we said in the first section. Okay, so let's take a look at this maybe one more time. So CO2 comes from mitochondria, so you're burning fat, you're burning sugar, maybe a touch of proteins, and the byproduct is CO2. And this gets released into the blood, and so your CO2 levels are going up. And part of the buffering mechanism, part of the exchange here is that it will go to the equation will go to the right, and the hydrogen will go up. So pH is coming down, right? Your acidity in the blood is starting to go up, and this will eventually clog up the system. You can only do this for so long before your muscles can't take it anymore and they stop functioning. So we need an exhaust mechanism. We need to get rid of the CO2. We need to get rid of the hydrogen. And so when the blood gets transported to the lungs, the whole equation operates in reverse. So we have high CO2 and high acid, but the lungs are blowing off the CO2. So the CO2 levels are going down, and so we backfill from the right side of the equation, and this is how the lungs lower the acid and the CO2 levels in our blood. So hopefully that's starting to make a little sense. So this is the exhaust mechanism for cars, for rocket ships, for power stations, for human bodies, for bacteria, right? I mean, this is like universal stuff. So if you put a potato in the exhaust pipe and you clog it up, if you stop breathing, for instance, and you prevent this from happening, your CO2 levels will stay high, and so will your hydrogen levels, and it's all going to back up until it reaches the muscle. And if it backs up to a level that's high enough, you're going to cut out the engine, right? So if you stick a potato in the exhaust pipe, even if you have good intake, even if you're supplying the engine with a lot of oxygen, eventually the CO2 levels are going to be so high that you're going to stop the engine from functioning, right? And it'll stop working. Sorry, just saw chat, the pH range 7.45 to 7.45. Yes, I probably have a mistake. It should be 7.35 is what it's supposed to be. So it's a very tight number. I've seen patients come into the hospital, they're kind of in the 6 range, 6.9, 6.8. That's a bad sign. That patient's not doing well. So just a Okay, so we're back here. So there's another place that we can kind of uh, suffer from this equation. So glycolysis. So we said CO2 comes from mitochondria. So where does the acid come from? That comes from glycolysis. And if you haven't seen our energy system talk, I'll show you where you can find it. But glycolysis will dump straight acid into the bloodstream. And so the acid will go up, and this will get buffered a little bit by this bicarb. So it'll combine with the bicarb to make this carbonic acid, and then this gets to get transported to the lungs in the bloodstream. And the same equation, same thing happens in the lungs. We have high acid, we have to get rid of it, and so the lungs are pushing the CO2 out, the CO2 levels are going down, and so you get a right to left shift in the equation. So now, what does that mean practically? Okay, so this is where, now that we talked about all this organic chemistry and nonsense, what does it mean for me in a race? Okay, so let's look at pH. So CO2, acid, these are kind of exchangeable things. It's the pH in your blood that's really going to determine these things. So if we put pH here on the side, and this is kind of where the race starts. Your pH is at 7.45 at a normal level, and you're doing okay, The acid is starting to build up, the hydrogens, the carbon dioxides, it's building, and all of a sudden you get this quick drop, and then you hit a wall, right? And everything stops working. So why is that? I want you to remember back in middle school, high school, you probably did a acid-base like titration experiment where you had a solution, it's like clear liquid, and it has a buffer in there, and you're dripping acid, and everything's fine, and the solution's clear, and then all of a sudden it turns pink, okay? So the way buffers work is that they only work for a certain time, and then they crash, and you get a big change in the pH level, you get a big change in the acid. So swimmers, that's what happens in a 200. They take off too fast, and they're not going to manage the end of the race with the level of acid in their blood. And if they go out too fast, they're going to hit that wall, and then they just kind of go slow from there on out. So how do we delay the wall, right? We want to push this wall off to where they're stuck in the caramel of the pool. We want to push it off as far as we can in the race. Well, breathing early and breathing late can have a really big difference, right? Because if you're breathing late, that means you've cut out your exhaust mechanism. That means you can't get rid of CO2 early, and that means your hydrogen is going to rise faster and faster than it normally would. Whereas if you breathe early, you can reverse all of that. So you keep your CO2 levels low in the beginning of the race, and that way when your acid is rising towards the middle and end of the race, it has somewhere for it to go. It has somewhere for it to buffer and to leave through the lungs. So again, the simplest analogy to think about is like it's just like an exhaust system. So if you're breathing late, you've got your exhaust system plugged up. You've got potatoes in the tailpipe. And what you don't want to do is you don't want to put potatoes in your tailpipe. You want to breathe early, and you want to breathe often if it's 100 or more. 100, you can get away with breathing a little bit, every 4, every 6, you play with it, but this is the biology behind. If you're looking at a swimmer, they're breathing every stroke off the walls, and you're like, how are they going so fast? Well, they're taking advantage of this mechanism, so it might be something to play around with. If you're doing a 200 and above, 100% you should be breathing as early as possible. There's another thing actually that I just thought of. A lot of swimmers, especially when they're young, they get taught to breathe every 3 strokes, right? So if you're breathing every 3rd stroke, that means you're more on the spectrum of holding your breath, right? And people do it for balance, and you don't want to cause shoulder problems. I get it. But as swimmers get older, I really encourage them to breathe every other stroke. So you choose one side that you like, and you breathe as much as you can onto that side. Why is that important? Well, you're getting 50% more breaths, right? So you're keeping the exhaust open 50% more often than if you were breathing every 3rd stroke. Same with butterfly. So if you breathe butterfly every stroke versus every other stroke, you're doubling the amount of breaths you're taking in that race. And especially in a race where you spend so much time underwater, you want to be able to, you want to do the gas exchange as much as you can above water. Once I kind of researched this and put it together, it really became clear to me that coaches yelling at swimmers to hold their breath all the time and don't breathe off of turns and don't breathe into and keep your head down. You know, okay, for a really short race, 25 and 50s, sure, go for it. I totally agree. Once you get over that 40-second, 50-second mark, if your race is taking 40 seconds to a minute long, you should be breathing early and often in all of these races, especially butterfly and backstroke, where you're spending a ton of time underwater doing dolphin kicks. Okay, we have reached the end. We got some questions on where you can find more of these videos. Let me show you. So a lot of this information came from this book here, The Biology of Swimming. And, you know, I like making PowerPoints, so I made a whole PowerPoint course for the whole book. Where is it? So you go to swimsmarttoday.com, courses, and there's a couple of them here. The Biology of Swimming course is what you'll want. So it's broken into 80, so it's 12 hours of video, and it's broken down into like 85 shorter videos. So they're all like 5 to 10. I think a couple of them are 15 minutes long. And it's this information, it's the one that we just talked about. These are all the topics here that you can see. There's quite a bit. We go into nutrition and a little bit of physics. You know, how does different training affect different types of biology to make you faster? Let me see if I can show you what this actually looks like. If you go to access my course, and remember to use that code webinar 20. Okay, so once you buy the course, you'll log in through this button, and then if you click the Biology of Swimming course, this is where they'll all be. So you can click on the different segments, and it kind of goes through all of the chapters and subsections of the book. So the one we were just doing is, here we go, lungs, breathing, and acid control. So there'll be like an introduction, and then I lost it again, moving the air, right? So that's, you can kind of tell these are the same PowerPoints. But if you want to just reference this video, if you go to our YouTube channel, now you're going to see what all the YouTube things that I like to watch. If you go to Swim Smart, it should pop up right here. So lungs and breathing, that's what we're doing now. This is our light bulb. So if you come to the light bulb here and you go to podcasts, this is where the playlist is found. You can find all the ones that we've done here: nutrition, energy systems, dry land. I think these are all still available. So I'll keep that up for a while, and hopefully we'll do these a little more often, and we'll see you at the next one. So thanks for joining, and we'll do this again sometime.